The oscilloscope. You're not expected to understand the construction of an oscilloscope, but it might help you understand its operation if you have some awareness of how it works. This is a diagram of the main components of an oscilloscope. This is an evacuated tube, and we'll start at this end, where we have a filament connected to a low voltage power supply. This will get hot, causing electrons to be so-called boiled off. We'll have a cloud of electrons around the wire. Next, we have a high voltage across here, keeping the filament negatively charged relative to the anode here, which is positively charged. The electrons which have been boiled off by the heated filament will find themselves attracted towards the positive anode. Many of them will pass straight through this gap towards these horizontally aligned plates. These plates are connected via an amplifier to the input potential difference, the potential difference we're trying to measure. If the top plate is made positively charged relative to the bottom plate, the electrons passing through will be attracted towards the top plate and be forced upwards. The degree of force given to the electrons relative to the input potential difference is controlled by this button. This is given in terms of volts per division on the screen. More of this later. Next, we have these vertically aligned plates connected to what's called the time base. What these do is move the electrons steadily across this way, then bring them back to the beginning. This knob here allows us to adjust the speed at which the electrons are moved across the screen, and this has the time usually in milliseconds per division of the screen. More of this later. As an electron is passing through here, if the plate nearest us is positively charged, the electron will be drawn towards us. Finally, the electrons will meet this fluorescent screen. The kinetic energy of the electrons hitting the screen causes a glowing in the screen, so we can see where the electrons hit. So, to see the oscilloscope in operation, I'll have this circle representing an electron, and it gets drawn towards the anode and accelerated towards the screen. In doing so, it passes through these plates and through these plates. I'll just do that again. You see, when the electron hits the screen, it makes the screen glow for a moment. One more time. The electron passes through the plates, hits the screen, and the screen glows. Of course, there'll be billions of electrons hitting the screen every second, so we'll end up with a permanent glow on the screen. This position is representing the situation if the plate nearest us here were positively charged relative to this one, and if these plates were neutral. So an electron would now pass straight through these plates, be drawn towards us, passing through these plates, and hit the screen at this side. However, as I said before, what the time base does is steadily draw the stream of electrons across the screen and then suddenly bring them back. So we end up with this sort of situation. The electrons are drawn across the screen, come back. If this is done fast enough, we get a line rather than just a dot. Now to examine the operation of these plates. If we make the top plate positively charged relative to the bottom plate, it will draw the dot up the screen like this. Reversing the charge on the plates would draw the dot down the screen. An alternating PD across these plates would cause the dot to go up and down and up and down. Combining an alternating supply across these plates with the operation of the time base would give a motion of the dot something like this. So basically what we have here is a graph of potential difference against time, and the situation I've just shown you would give a graph something like this. The oscilloscope has a very high resistance and so makes an excellent voltmeter. Let's look at the operation of the oscilloscope as a voltmeter now. Here we have an image of just the screen of the oscilloscope, with squares running horizontally and vertically. The boxes here tell us the settings of the Y gain and the time base. So we have a Y gain of 0.5 volts per centimeter, which means a input potential difference of 0.5 volts would move the dot 1 square or 1 centimeter away from the central position. So here we have a peak voltage of 0.5, 1, 1.5 volts. So we can write that the peak voltage is 3 centimeters multiplied by 0.5 volts per centimeter, the setting here, giving a peak voltage in this case of 1.5 volts. To find the frequency of the supply, well, first we can find the time period. If we go from the peak here, for instance, to the peak here, we need to cross 1, 2, 3, 4, 5, 6, 7, 8 squares, or 8 centimeters. And so the period is 8 centimeters at 10 milliseconds per centimeter, meaning a time period for this supply of 80 milliseconds. Frequency is found from 1 over time period, or 1 over 0.08 seconds, meaning this supply is at a frequency of 12.5 Hertz. Here we have a different supply, but you'll notice the Y gain and the time base are at the same settings. So now we have 1, 2, 3, 4 centimeters at 0.5 volts per centimeter. So the peak voltage is 4 times 0.5, meaning 2 volts. The time period, well, going from this peak, we have to go 1, 2, 3, 4 centimeters to this peak. So the period is 4 centimeters at 10 milliseconds per centimeter, or 40 milliseconds. Frequency is 1 over time period, which is 1 over 0.04 seconds, or 25 Hertz. When you have smaller waves like this, it can be helpful to measure the time period across several. Another supply now, and now the settings have changed. Now the Y gain is 1 volt per centimeter, so the peak voltage is 1, 2, 3 volts. So we can write the peak voltage 3 centimeters at 1 volt per centimeter is 3 volts. Time base at 50 milliseconds per centimeter, and the time period now, we'll have to start from here, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 centimeters. So time period is 12 centimeters at 50 milliseconds per centimeter, which is 600 milliseconds. So the frequency 1 over the time period, or 1 over 0.6 seconds, giving a frequency of 1.7 Hertz. Another supply, and the peak voltage 1, 2, 3 centimeters at 1 volt per centimeter, meaning a peak voltage of 3 times 1 volt per centimeter, 3 volts. The time period 1, 2, 3, 4, 5, 6, 7, 8 centimeters at 50 milliseconds per centimeter, meaning the time period is 400 milliseconds. The frequency 1 over the time period, 1 over 0.4 seconds, meaning a frequency of 2.5 Hertz. Another supply, same setting here, 1 volt per centimeter, so the peak voltage now is 1, 2, 3, 4 centimeters at 1 volt per centimeter, meaning a peak voltage of 4 volts. The time period, well, now we can go from here, 1, 2, 3, 4 centimeters. So the time period is 4 centimeters at 50 milliseconds per centimeter, time period of 200 milliseconds, or a frequency of 1 over 0.2 seconds, which is 5 Hertz. A new supply and different settings. So now we have a Y gain of 0.2 volts per centimeter, and a peak voltage going 1, 2, 3, 4 centimeters up. So the peak voltage is 4 centimeters at 0.2 volts per centimeter, giving a peak voltage of 0.8 volts. Time base at 20 milliseconds per centimeter, and a time period of 1, 2, 3, 4 centimeters. So the time period is 4 centimeters at 20 milliseconds per centimeter, or 80 milliseconds. The frequency 1 over 80 milliseconds, or 0.08 seconds, giving a frequency of 12.5 Hertz. And finally this supply with a Y gain of 0.2 volts per centimeter, peak voltage going up 1, 2, 3 centimeters, so the peak voltage is 3 centimeters at 0.2 volts per centimeter, or 0.6 volts. The time base at 200 milliseconds per centimeter, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 centimeters, meaning a time period of 12 centimeters at 200 milliseconds per centimeter, which is 2400 milliseconds, or 2.4 seconds. The frequency then 1 over 2.4 seconds is 0.42 Hertz. If we applied a DC supply to the oscilloscope, we might see something like this, with a horizontal line running across the screen. I've given a different colour here just so you can see where the line is. In this case, the time base is not important. The Y gain of 0.2 volts per centimeter shows that the line is 1, 2.5 centimeters up, and so the potential difference is 2.5 centimeters at 0.2 volts per centimeter, or 0.5 volts.